In this session, I will be demonstrating the DC sweep analysis using the Allegro PSPICE simulator. I will be demonstrating this particular analysis by constructing a circuit for common emitter configuration of an NPN transistor and then simulating the results. I'll create a new project. I'll name it as NPN characteristics. I'll make sure the type of the project is PSPICE analog or mixed AD, and I'll save the location of all the project related files into a folder. I'll create a folder on the desktop. I'll name the folder as NPN. I'll select that and then I press OK. And having verified the type of the project I would like to construct is PSPICE analog or mixed AD, I press OK. Here I would like to create a blank project, so select the create a blank project option and then press OK. It will take you to the schematic window where we shall start by placing the parts. So first and foremost is the transistor itself. So I press P from the keyboard to enable the place part window and I'll search for the transistor. You should know the transistors are usually denoted by names that start from Q in the library files. The one I am currently interested in is Q2N2222. You see, it is a BJT, it represents bipolar. So double click on that and place it here. I'll zoom in a little bit. Right. After this, as you know, we require two resistors, one across the base and another one across the collector. So search for R analog, double click, place one here. This will be R1, this will be R2. Further, we require, since the type of the analysis I am going to conduct is DC sweep, two DC voltage sources. So I'll search for VDC, select VDC source, place one across the base, another one across the collector to emitter. I require a ground, but I'll connect it after completing the wiring. So let us start wiring by pressing either W from the keyboard or pressing this icon here, and I'll start connecting the components. Right, the connections are done. Now I'll place the ground. I'll select 0 caps in. Once again, I need to connect that to the circuit as well. Now I will change the names of the resistors and DC voltage sources for my convenience. I'll call this as RB, base resistor. Let this be RL, the load resistor. This will be VBB. And this will be VCC. Right. So having done that, we have completed the circuit construction. We are ready to simulate. Please note, I have not given any values for the voltage sources across both the base as well as across the collector, because I can vary these values directly using the simulation profile. If you want to, however, put some values for steady state conditions, I'll suggest 3 volts for the VBB and 10 volts for the VCC. They are sufficient. You can obviously have different values as well. Now, after having constructed the circuit, the next obvious thing is to construct a simulation profile, and to do so, I'll go to PSPICE, select new simulation profile. I'll give the name as NPN common-emitter CE, create it. A new pop-up window will appear, select that. Now change the analysis type from time domain to DC sweep, right? So when you change that, you will immediately see the interface changes, and in the options menu, the primary sweep is always selected, you cannot deselect it. Okay, so that is one thing. Now what we will do, we will first start by demonstrating the input characteristics of the NPN transistor. We know that input characteristics is a plot of the voltage across the base to emitter terminal with respect to the base current. You should note the variation across the base to emitter voltage can be brought upon by varying the voltage across the input, which is VBB. So you select that as the primary source. Coming back to the simulation settings, you already have selected the primary sweep and the type of the sweep variable is voltage. So you select voltage source across the sweep variable and give the name of the variable. Here the name is VBB. So you type VBB, fine. Now coming here, you have the sweep type. You want to start the variation from, let us say I'll start from 0 volts and I'll continue the variation till 3 volts. As you should know, this is a base to emitter junction. So we already have set the collector voltage as 10 volts. So it would require only around 0.7 volts to break down. But still I have kept the end value to 3 volts because I just want to show you the variation of base current with respect to base to emitter voltage, right? And the most important thing here is the increment. Like in the sense, when you are plotting the waveform, you start recording the value of the base current at one value of VBE, then increment to the next value. So this increment to the next value is what you are supposed to give here. If you give a very high value, such as if I give 1 volt here, then you will only obtain 4 readings, each at 0, 1, 2 and 3 volts. So these readings may not be sufficient enough to plot a neat input characteristic curve. So try to give a smaller value as increment, such as 0.01 volt, which will create a very fine input characteristic curve. Right? When you are ready with this, you can apply, press OK. Simulation profile is created, circuit is ready. Now we will run the simulation. Again a pop-up window appears and you see the simulation window appears. Now before I talk about the simulation results, I would like to tell you one thing. If there are any errors in the construction of your circuit, then you will never be able to open the simulation window. For example, I'll introduce an intentional error such as not placing the ground. So I'll remove the connection between the circuit and the ground. I'll run the simulation. Now you will see you will be taken to the simulation window, but instead of the waveforms, you will be shown the connections and errors across the same. You can reconfigure the circuit depending upon the errors and then once again come back and simulate. Now let me just connect the ground once again to the circuit and run the simulation. In the simulation window, I start by tracing. So what I'm supposed to trace? I'm supposed to trace the base current. So go to trace menu icon, select add trace, remove the aliases, then you will be left out with the most possible options. What I want is the base current. So you select IB of Q1, then press OK. You will see the characteristic curves is appearing, but most importantly you should note the parameter across the x-axis is not the base to emitter voltage, but it is the VBB. So you need to change this. To change this, double click on the x-axis. Axis settings window will appear. Select x-axis, select axis variable. Again I am removing the aliases and now I want the voltage across the Q1 base. So you select V, Q1 is to base, press OK, press OK again. Now you will see you are now obtaining the input characteristic curves of the NPN transistor. So this is our origin and the transistor is triggering somewhere around 700 millivolt, which is 0.7 volts, right? So this is how you are supposed to obtain the input characteristic curves of the transistor by performing a DC sweep operation. Coming back to the schematic, we most of the time perform the input characteristic curves at multiple values of VCC. You can do so by changing the simulation profile. Now to change the simulation profile, you need not always come back to the schematic window and edit the simulation profile. You can do so directly from the simulation window as well. So go to the simulation window, select the simulation menu item and select edit settings, right? So here what has happened, the primary sweep variable was the VBB, which was base voltage, and we had selected the value of VCC as 10 volts constant. and in fact the graph we are looking at is for VCC of 10. Right. So, if you want to obtain multiple input characteristic curves at different values of VCC, then you need to perform what is called as a nested loop operation. It is also called as nested sweep. To perform the nested sweep operation, you need to select the secondary sweep option as well. And now what you want to vary? You want to vary VCC because the primary sweep variable is VBB and it is already being varied here. So, select the secondary sweep. You want to vary VCC here. So, give the name of the variable you want to vary here. Then here you are supposed to give the range of the variation. I would only require 3 curves. So, I will start from somewhere around 0 and let the end value be 100 and I will increment it by 50 volts. So, now what will happen? I will get 3 input characteristic curves, one at 0, another one at 50 and last one at 100. Right. So, let us apply this and rerun the simulation. I will add the trace once again for the base current, that is IBQ1. Now, the x-axis needs to be changed because currently it is depicting VBB. Right. So, now you can see we are obtaining 3 characteristic curves. So, the rightmost curve what you are looking at is for the value of VCC equals to 0 volts, and as the value of VCC is increased, the characteristic curve starts to shift left. So, this is for 50 volts, and the last one what you are looking at, which is actually triggering at around 0.62, is for VCC equals to 100 volt. If you want to mark these parameters on the profile itself, you can go to text label and enter the text of your choice. For example, I will write VCC equals to 0 volt and I will place it just above the last curve. Then again I will add another text label and I will write VCC equals to 100 volt and I will place it here. And very similarly, you can place as many text labels as you want on the simulation window. So, that is about the input characteristic curves of the transistor. Moving on to the output characteristics. Output characteristics are obtained by plotting the voltage across the output terminals, that is collector to emitter voltage, and recording the output current IC at a fixed value of the input current IB. We know that a transistor output characteristics indicate 3 regions of operation: cutoff, saturation and active region. So, let me demonstrate the simulation of the transistor here by setting 3 different profiles for each region of operation. I will start with the cutoff region. So, to set the profile for the cutoff region, I will go to PSPICE, edit simulation profile. Let the primary sweep variable be VCC. Let it vary from 0 to 10 volt in increments of 0.01 volt. And the secondary sweep variable has to be compulsorily VBB because I do not have IB as a parameter here. Right. So, what I will say, I will vary VBB and therefore the IB will vary. So, it is quite linear in fashion. So, if I set VBB as a secondary sweep parameter, it is still fine. So, I will vary VBB from 0 till a value which is not sufficient enough to forward bias the base to emitter junction, which is, let us say, 0.5 volts, and I will increment it in terms of 0.1 volt. Right. So, now I will expect at least 5 characteristic curves starting from 0 till 0.5 in increments of 0.1. So, let us apply these simulation settings and run the simulation. I will add the trace for the output current, which is the collector current here, and I will change the x-axis from VCC to voltage across the collector to emitter, which is VQ1C. Right. So, when you look at this characteristic curves carefully, you notice that the current across the y-axis is in the microamperes range, which immediately should mean the transistor is currently operating in the cutoff region of operation. Now, moving on to the next, we have the saturation region because the current has to rise and this rise across the current is usually seen across the saturation region. So, in order to do that, I will now change the simulation profile, and I will do this directly from the simulation window itself. So, go to the simulation menu, select edit settings. Here I will keep the primary sweep variable same, no change in that, but the secondary sweep variable, which is VBB, I will increment it from 0 till a value which is greater than the new voltage. So, let us say 2 volts, and then let it be incremented in terms of 0.5 volts. So, I am expecting 4 curves starting from 0 till 2 in increments of 0.5. Let us apply and run the simulation. I once again add the trace for the collector current, and I change the x-axis to collector to emitter voltage VQ1C. Now, as you can see, you are obtaining several characteristic curves, and these curves are represented by lines which are almost parallel to the y-axis. So, this in fact is the region in which the transistor is currently operating, and we say this region as the saturation region of operation. Now, what has happened here is that the transistor has gotten stuck in the saturation region and it is not entering the active region at all. Now, however, to simulate the transistor operation in the active region, I will once again change the simulation settings, and primary sweep variable, now let it vary from 0 to 100 because I want the transistor to enter the active region, and the secondary sweep variable will be kept constant, no change in that. So, you will get once again 4 curves. Let us apply, press OK, run the simulation, trace the collector current and change the x-axis to VQ1C. So, now by looking at the characteristic curves, you understand only one particular characteristic curve has entered the active region and remaining all curves are still in the saturation region. Now, this is mainly because the values of the base and the load resistances are kept equal in our circuit. In fact, I intended to keep in this particular way because I wanted to show what is the importance of those resistances in sending the transistor into active region. If you want to plot a very clear-cut output characteristic curve in the active region of operation, you need to change the value of RB. This has to be a little greater. For example, I will change it from 1K to 5K. I will rerun the simulation. I will add the trace once again, and I will change the x-axis to VQ1C. Right. So, now you can see you are obtaining 4 characteristic curves, right. So, this is how you will obtain the output characteristic curves of the transistor. Lastly, I will demonstrate the transfer characteristic curves also. Transfer characteristic is obtained by plotting the voltage across the input terminals, that is VBE, and recording either the output current IC or the voltage across the output terminals VCE. In order to obtain the transfer characteristic curves, I will once again change the simulation profile. I will remove the secondary sweep because now you only need to vary the primary input voltage, which is VBB. So, I will select the primary sweep variable as VBB and I will vary it between 0 to 2 volts. This is quite sufficient enough because the transistor would turn on at 0.7 volts and therefore 2 volts as the end value is justified. And increment, let it be 0.01 itself. Apply, press OK, run the simulation once again. Now, you need to plot the output current. So, go to trace, add trace, the collector current IQ1C, but the x-axis is VBB, you want VBE. So, change the x-axis to VQ1B, right. So, as you can see, you will obtain a S-shaped curve, and this in fact is a variation of the collector current with respect to base to emitter voltage. Another way of plotting the transfer characteristic curve is by plotting the collector to emitter voltage by varying the base to emitter voltage. So, I will put that plot in a different plot area. So, go to plot, select add plot to window, and here you left click and then trace the collector voltage, so which is VQ1C, right, and immediately since the x-axis is extended to the upper plot as well, you can see that the variation of collector to emitter voltage is inversely proportional to the variation of the collector current, which means as the collector current rises, the collector to emitter voltage drops, and when the collector current becomes maximum, the collector to emitter voltage becomes minimum. Right. With that, we come to the end of this session. To summarize, a DC sweep analysis is conducted for circuits in which the type of the input voltage source is DC. Here, you will be varying the values of the input voltage source by giving a range and then incrementing the same by a finite step size. If you like this video, kindly like and subscribe to my channel for more information. Thank you for watching. Have a good day.